Thank you everyone for watching. So we are here today to talk about the Digital Building Executive Master of École des Ponts in France. You can see my screen. Yes. So I will present briefly the master, and then we have invited some past students to talk about their experience with the master and their thesis. So the Digital Building Design Executive Master is about computational architecture and engineering for design and for fabrication. It is a place where designer, engineers, architects, and researcher gather together to communicate and learn about innovative practice of this industry. The picture that we have behind us today is a recent prototype that is on the campus of the school that illustrates some of the outputs that this kind of studies can have about computational design and computational fabrication. So this is something that happens on the inside the École des Ponts engineering school, where we have a platform of fabrication with robots that you can see on these pictures that help us work with various materials, wood, concrete, clay, to do innovative prototypes for construction. This picture illustrates a very important theme that we call construction-aware design, when we try to ease the construction of complex geometries with the help of mathematics, geometry, but also innovative prototyping. It's also a place when we do architecture in an innovative way. You can see here the results of one student's thesis. That's an illustration on circulation optimization inside the project. So the master is 1 year and a half, but exactly 1 year courses. You have first 4 months of full-time courses inside the school to learn the tools and to learn the theory behind all of this. And then the second semester, you go in a company and you work part-time at school 1 week a month to do either computer-aided manufacturing workshops or computer-aided design courses. So just to give you some examples of what we can do with manufacturing. So there is a workshop on robotics, on large-scale 3D printing, on wood, on innovative assemblies, and something linked to reuse. And we also learn architectural geometry, machine learning, optimization, and innovative structural studies with form finding. So this is just a glimpse of what we do, but I think the best is to let alumni talk about their experience and show what they have been studying. So I think, so Leah, unfortunately, will not be able to be here, but I think we can directly go to Julien, if we keep the order, and if you are okay, Julien.
Thank you, everybody. So my name is Julien Perard. I'm a French engineer, and I just finished the Master of Digital Building Design in December. And I'm gonna present my research project that I did under the supervision of Maurizio Brocato, who was a professor in the school and a director of the laboratoire GSA. Well, so my research is about Gothic vault, and the idea was to develop a parametric model of quadripartite rib vault, taking stereotomy into account. So by modelizing the vault as an assembly of discrete elements, which are the stone. And this research was made in the context of the renovation of Notre-Dame de Paris. So masonry vaults are one of the most important and common architectural and structural elements of historical buildings in Occident. These vaults are characterized by their curved geometric shapes and the ribs that support them. I don't know if you see my pointers, but well.
Yes.
Yes, we see.
Okay. So which make it possible to cover large spans while ensuring that the structure made up of ashlars works mainly in compression. So if the structures are commonly found in our built heritage in Occident, their restoration remains complex due to their curved geometric, the stereotomic know required, and the structural modeling. So here you have the clue point of Notre-Dame de Paris. And indeed, the use of digital technology has allowed a more precise modeling and a better understanding of the structure. For example, with the clue point, you can have access to a very precise geometric information that you can use for your 3D model. For example, on the left, you have the result of a parametric process which take as input the geometric data obtained from a clue points and make it possible to model the geometry of any rib vault and to export it in a finite element analysis software. So you can see this model is really precise in terms of global geometry, but we don't have the representation of each stone, of each ashlar, and so it's not a discrete model. On the right here, in contrast, you have a work which are focused on discrete and discrete structural modeling. However, the geometry of the vault is not based on a clue point, and the stereotomy is simplified. And so de facto, this model is aimed at theoretical purpose and is not really suitable for a practical case. So in our opinion, the structural understanding of the vault cannot be done without a geometry faithful to the existing one, like in the model of the left, and also a representation of the stereotomic characteristics or discrete assembly of the vault. And so we worked to produce this kind of model. So the first step of our algorithm was to define fundamental geometry of the vault. So the most general way to define a quadripartite vault is to consider 6 arches on which rest 8 masonry panels. On this drawing, you can observe that we have 2 planes of symmetry in XZ and YZ, which passes through the center of the vault. So we can restrict our problem and to just one quarter of the vault. So in an ideal case, this geometrical information can be obtained directly from a clue point, or we can play with a lot of parameters to modelize different types of the vault. So here just an example of the tips of arcs that you can find in the Gothic construction. there is a lot. And here some example of the result for the fundamental geometry. So the second step is the modelization of the intrados of the panel. So actually the surface of the web. So actually in Gothic construction, the panel are most often curved so that the blocks rows form arches, which make it possible actually to transfer the force of the webs to the ribs while facilitating the erection of the vault. So we implement this in the algorithm by curving the loft surface. And next, we have the stereotomic design. So the first step was to modelize the voussoir of each ribs, which is not so complex. We have some topological complexity also to take into account, but I'm not gonna dive into this. And the second step is the tessellation of the intrados surface. So for this, we use Chebyshev net, which has a property of preserving distance between points on the surface, and which correspond to Gothic construction rules in a sense where the mason fills the webs of the vault with a rectangular stone of homogeneous dimension. And so we have this brick pattern on the right. And the next step is a question of the ogive. The ogive is the diagonal ribs. In the literature, you can find actually two types of ogive. One with rabbets, and one case on the right, which is the traditional case. And I'm gonna focus for the presentation only on the case of the right. So actually, the complexity for these types of ogive is the junction of the panels of the webs on the ogive. On the literature, we can observe some debate actually. For some authors, the panels will meet frontally like this and are forming a continuous joint. And for some other, there is an interlocking system of the stone on the ogive. So to kind of settle this debate, we observed existing vaults and try to understand how they have been built and what is the stereotomic port. So for example, here you can observe the intrados of the vault, and we can see that there is a kind of interlocking pattern. We also observe it on the extrados of the vault of the Cathedral Notre Dame. But what we finally understand is that it's not a global system, it's something more local and directly made by the stonemason during the erection of the vault. So we try to reproduce this interlocking system in an algorithmic way according to local parameters. And finally, we start from this, and we obtain this geometry where we can find the main characteristics that we observed on the existing vault. Then we start the projection definition. So the idea is to define a global projection system in order to obtain a volumic model. So we base this algorithm on historical study or on what we observe in the existing. And here, for example, you have the surface of the joint. And finally, the volumic model. And here an example of an application. So we start from the clue point. This is the clue point of the Basilique Saint-Donatien in Nantes that I did myself. So it's not really really precise, but it's okay for the example. And here you have the superposition of the model with the clue point. So it's not perfect in a mathematical way. I don't run optimization algorithm to fit perfectly, but we can see that it's quite okay. And finally, there is export to the finite element software, which is a custom. And here you can see the meshes of the blocks, and also in red, the meshes of the joints to allow the sliding of the block or stuff like this. So discrete model. And finally here an example of the deformation and the von Mises stress. I have to mention that is a continuous model because the calculations are quite heavy for a discrete model. And I think I am 1 minute too long, but so I stop here.
Thank you. Perfect.
Thank you very much, Julien.
But good morning, everyone. I would like to thank Romain for giving me the opportunity to introduce Pulp. But before I start telling about Pulp, I will briefly introduce myself. My name is Lorenzo Fauvet. I'm an architect. I have an atypical path because for more than 10 years, I have been dedicated in a large architectural project in an architectural firm. And throughout my professional career, I have become increasingly interested in new technologies related to architecture, design, art, and how to make these activities more sustainable. After a few years of being self-taught, I decided to follow an education that could advance in my exploration. And so I decided to attend the Digital Building Design Master Program. And as part of the master program, I carried out research in collaboration with X3 on a 3D printed concrete acoustic wall. The focus of this research was to be able to design and fabricate through robotic 3D printing and computational design tool a self-supporting acoustic wall that improved the acoustic qualities of a room through acoustic diffusion phenomena. Computational design and robotic 3D printing combining in a single workflow enable seamless digital design and fabrication, minimizing errors. Sorry. Once the design and printing parameters were established, I was able to print a prototype of a portion of the wall in order to validate my investigation. From this experience was born Pulp for Plastic Loop, a young startup created just under 2 years ago. Pulp, it's two founders. One is me, and the other is Thomas Sicuri, also architect and digital building design master alumni. Pulp was born from a simple question. How do we value the mountain of plastic waste that human activity produce every day? The idea is to be able to use plastic waste as a new raw material, because we are all aware of the problem of plastic waste and its negative impact on our planet and our health. And we are all aware that this problem is largely generated by economic model, linear model based on mass production. Pulp in 2022 winner the best innovation for additive manufacturing addresses this issue by using plastic waste as a raw material for a circular and sustainable additive manufacturing. Pulp is a new urban microfactory specialized in a large 3D printing, in a large scale 3D printing, sorry, and ecological transition. The microfactory is a small production center located in the dense urban landscape to boost the local economy and create synergies between the different actors of the circular economy sector. Each microfactory is composed of several additive manufacturing units. It's the 3D printer machine, capable of transforming plastic waste into high-value added product. With Pulp, we want to reshape the additive manufacturing industry, shifting toward a more sustainable and post-carbon future. We offer a co-design service and fabrication service. We accompany our client throughout the creative process, from the idea to its realization. We work in synergy with our customer to create a unique solution design, tailored and manufactured in France. Actually, we have realized the first prototype of the additive manufacturing unit is the 3D printing machine. We took existing industrial machine and transformed, adapted, and assembled them to create our 3D printer, which consists in a printer head mounted in a 6-axis robot that by moving, it's able to transform a more or less complex virtual geometry in a real object with precision and speed, and an industrial extruder into which the material is fed. This system allows the use of a wide range of post-consumer and post-industrial plastic waste. We can use almost any thermoplastic polymer. Unlike commercially available 3D printers, we don't use filament to print. We feed directly shredded material. You can see this in the photo. This has many advantages in terms of environment and cost, because our material is less processed and cheaper, and we can print faster. Now, currently, we use mainly post-industrial waste from food and pharmaceutical packaging. Here we have, you can see 3 different tests. These tests were done to find the optimal printing parameters and understand how the material reacts, and understand also the limit of our system. These 3 tests, it's made of different scale. The first one, it's 20 centimeter of high. The second, it's the double, it's 14. And the third test, it's the big one, it's almost 2 meters. It's a lampshade, the last one. Here you can see an artwork we made with an artist in the photo. And this work was exhibited in an artist festival in Paris area. You can see the video. It's accelerated. We don't print so fast. We have another video, sorry. Oh, sorry. Yeah, this is a real speed. And this is the first POC, proof of concept we made. It's a stool. And for us was very interesting because it's the first time we print a big object after a month of research. It's speed, but it's not so speed. And the last, it's thank you, everyone. And if you are interested in getting some news about us, you can follow us on LinkedIn.
Thank you, Lorenzo.
Thank you very much.
Unfortunately, I have to go because I have another meeting coming up.
Okay,
I'm
don't
so
worry.
sorry.
Thank you very much, Lorenzo, for sharing this with us.
Thank you, Romain. Thank you, Geraldine. Ciao.
So maybe we can keep on presenting unless somebody wants to ask something, but
Yes.
maybe we will have questions by email after this recording.
Yes.
It's possible for us to answer one by one. Kritika, would you like to?
Yes,
Yeah,
of course, I'm here. Yeah.
Thank you very much.
So I'll just share my screen. Just a second. Okay. I hope it's visible.
Yes.
Okay. All right. Perfect. I'll go on. Hello, everyone. I'm Kritika Walia. I come from India, and I'm an architect from there who worked in Delhi for 5 years. And after that, in 2019, I came here to Ecole des Ponts to attend digital building design, and I finished my master in 2021. Currently, I'm working at Ecole des Ponts itself at building co-innovation lab as a research assistant. And today I would like to share my thesis work and my professional journey after 1 year after the master. So, yeah, at DBD, my master thesis was about building a concrete shell using fabric membrane and telescopic arches as the formwork. So as we all know that building complicated structures like these with double curvature, especially, it's quite difficult to fabricate. And mostly it's because of their formwork system. And since their formwork is unique, it requires a lot of material which goes to waste generally after a single use, and hence it's not sustainable. So my idea was the hypothesis was to basically have the shell forms, especially negative curvature, that can be built out of fabric as a formwork material, and I intend to reuse it. So the key features of my project were that it should be a hybrid. It will have to be a hybrid formwork because I need to hold the fabric somewhere. Then it should be removable and reusable, of course, and the entire system should have a quick and easy disassembly with the simple connection systems. So we proposed this idea along with the telescopic arches, which can be smoothly removed from under the built structure, which I'm going to talk about in next slides. Actually, I'll be showing a video in which it will be much clearer. So next, to support my hypothesis, I developed a basic saddle form, basically 2 saddle forms connected to each other. And I did structural tests digitally in order to check the behavior at different stages. And the stages being first at the assembled formwork. So it includes basically the fabric formwork, the telescopic arches, and the cables to counterbalance the entire formwork. Second, second stage was about spraying the concrete over it. So we did this tests during that time as well. And third was after the formwork removal when the concrete was completely set. So the aim was to indeed have a durable structure at the end. So at the left, you can see the assembled formwork that we did. And at the right is an image taken during the concrete spraying. Over here, if you see my pointer, you'll be able to see that these are the telescopic arches. Then after the formwork, after having removed the formwork, this is how it finally looked with the sleek edges, and it had a complete raw concrete finish inside. I also prepared a catalog of proof of concepts as well, basically more sort of designs that are possible to do with this specific technique and the repetitions that are possible. So it could be linear format or polar or rotating format. So an array as well. So that is what I was trying to develop, looking from the architectural point of view. So to conclude, I would say that it has this technique is a potential design and construction model which provides design flexibility, innovative shapes, along with the structural data, especially relevant to a designer. So now you can see the video, which will show better how the telescopic arches work. So this is how the telescopic arches were coming inside. So it's basically made of a For that, it provides grid shell canopies. The canopy you just saw in the video, they come with the creeper plants mostly, and they are basically proposed to be planted in the areas like open parking spaces, especially where there's a completely concrete floor and there's no possibility to plant a tree. So my role for 7 months was to assist the research of different fabrication systems, do design concepts for them, and propose different architectural applications. So largely, I worked on 2 projects over there. One was this one, a grid shell in angular sections, which was presented at CES Las Vegas last year in January. So it's basically a lightweight deployable grid shell made in angular sections, as mentioned, and as it's visible. So it can be used as a doorway or a porch, that sort of thing. So the prototype that we made was as large as to accommodate a car. And in the folded state, it was not even 50 centimeters wide, and the length was only 2.5 meters, which will be definitely varying depending upon the size of the structure. And it takes only 5 minutes to deploy it on site. So whether you can use it permanently or temporarily, that depends upon the application again. Secondly, I worked on a conceptual anti-clastic pavilion made in cable net system, which is indeed, again, lightweight and neat and carry huge loads. So for both of these projects, it was highly important to be sure of their load-bearing capacity and mechanical tests. They were a great part of the development. So now, as I mentioned earlier, I'm a part of Build-in Co-Innovation Lab at Ecole des Ponts. It's a R&D platform in digital construction, as Roma also mentioned earlier. And our wide variety of work is based on using robots for construction, for both additive and subtractive manufacturing. And not only that, we love to work with innovative or novel geometrical concepts. So in September last year, we organized a week-long workshop with a group of students of the NPC, and this is the same pavilion as our background image. So it was held at ENPC with some students of the school itself and some students of the School of Architecture in the campus. And we built a 4x6 meter huge pavilion with the concept of pseudo-geodesic lines. So it's a specific sort of geometry that is mathematically developed and implied. So for now, I'm not going to go into that detail, but I'll briefly talk about the fabrication system. So it consists of 2 layers of lats, or let's say planks, long planks, straight planks basically, which are inclined at 30-degree angle, each to the normal of the base surface. And this mesh is connected then to the wooden periphery around here. And the rotating connector over there at each node, which is now patented, was designed. It's one sort of connector which is which can be used for all the 150 nodes that are there. And over here on the right in the image that I'm pointing at right now, the dark blue Z's are the connectors cross section, and in the light blue, basically these Z, they hold the planks, and the light blue shows the location of the planks, and the two Z's are basically capable of rotating along the orange axis. Okay, and these planks, we can choose any material, but for our case, we used glass fiber reinforced polymer. These are a few images of the construction, during the construction process images, basically, and it was built just within 2 days after 3 days of theoretical classes. We spent 1 day in the atelier, in the workshop, to do the starting connections and prepare everything. And we spent 1.5 days at the site just to assemble it all together. We also work extensively with the 3D printing with the robots, using a wide variety of material composition, for instance, clay and concrete mostly. And these are a few examples of the recent tests that we did for our, that we are doing basically for our upcoming projects. Also, we work with laser scanners and motion capture systems and a lot more high-tech things to support our research. They basically help in detecting and recording deformations and movements in the real time in the structure. I'd like to wrap up my presentation showing one of the projects that Roma also mentioned in his slides. So this was done by the alumni of 2021 itself, Sukumar Vedachalam, and I'm going to show you the YouTube video of his project. I hope you're able to view it.
Yes.
So this is how we did the entire grid shell first on the floor, on the ground. We connected it with the special connectors that again come from Urban Canopy. And of course, special coding and everything is required. Then these steel plates were used as the edges to demarcate the shape. Then we put it in place and connected it at the edges to bring it into the correct shape. So first the grid shell was completed. And after that, the idea was to spray concrete again to make it a permanent structure. That's him. And this part of the video shows how the geometry was developed. And after that, of course, we put the mesh before spraying the concrete. Yeah, so that's all from my side. I hope you enjoyed my presentation. Thank you for your attention.
Thank you, Ritika.
Thank you very much. Yes, so I guess we can go with Felipe.
Yes.
Thank you very much, Felipe.
Okay, so I am Felipe. I come from Colombia. Right now I live in Paris, and I was part of the digital building design program in 2021. My project, the project I chose was focused on the generation of a framework, a digital framework to create an optimized slab system, focusing on trying to improve gathering the potential of many digital tools and create a framework that uses these tools to design a slab within the constraints of the fabrication, of the digital fabrication of the pieces, as well as taking into account the constraints of the building itself, of the construction of the slab. So this was my concept, initial concept, to gather some information from a simulation, just to gather some data from a specific structure, and use that data to generate the shape and to inform the shape itself, and then use some kind of digital fabrication method to fabricate this shape, and taking into account, as I said, the different steps of the construction process and how they inform the shape as well. So by that time, I started my internship at X3, the pioneering company of 3D printing in concrete in France. Here, there we developed the oriented-less pressing system to print large-scale structures in a workshop, and this technique has a lot of constraints and capabilities to generate and fabricate different kinds of shape. So I'm taking into account the possibilities of the system, and I'm also taking into account the building system itself, the limitations and the constraints, as the transport, the shoring, which means how the pieces are put in place for the casting, and then the casting itself. Well, in my project, I study and reference many different techniques, like digital fabrication, printed conwork as printed pieces as formwork for concrete structures. Also, the study of different patterns to optimize the shape of the slab, and a recent project from a university in Germany that has a similar approach. So the design framework I created has 3 main steps. These ones include first the optimization of the shape, then how it translates into the pieces I want to create, and additionally at the end, within X3, I developed with the help of the engineers at X3, I developed a simulation system that takes into account the early age mortar behavior to try to optimize either the shape of the shapes I want to print or the printing time, and to simulate the printing process. So first, I just have a random scenario, which in this case is just a very simple structure. From it, I gather some information from a structural analysis, And I use the technique described by the paper of Oval to recreate the same pattern within a discretized and easy to manage pattern. In this way, I can explore different iterations and different densities of this pattern that I can study and evaluate in order to optimize the structure. When I have this pattern, from it, I can generate the formwork or the voids where I will cast the beams of the slab. Here I take into account one of the first limitations or constraints of the building system. For example, I want to know if I should stay with a constant height for the whole slab, taking into account that this will make the shoring that we see on the right, as well as the transportation, very easy. But so that's for example, the first thing I want to discover, if I should keep a constant height or not. So to discover that, I start my exploration. I generate some initial patterns. Then I recreate the skeleton meshes to be able to explore them. And then I generate the different densities for those patterns. Then from those axes, I parametrically generate the information of the finite element analysis. And with it, I explore and optimize within some constraints how the dimensions of the beams should be in order to optimize the structure, meaning to have a good stability while reducing the mass of the slab, therefore reducing the weight of the building and the usage of material. And I recreate the same process, optimization process, with the whole spectrum of shapes that I created, that I am exploring. And from that analysis, I got this. I explored 3 different conditions for the height that I want to respond to that formal constraint. And as we see, the 2 options that indicate a variable height, that are represented with triangles and with the squares, we see that they have the less displacement, meaning the structure is not does not deform as much, while also keeping a low mass and overall low weight. But the price I'm paying for that is that I need to increase my height. But in general, I decided that okay, it's worth the extra effort into creating variable height elements that I will show you then how that informs my my shape of the slab and the 3D printed pieces. So I get the result from my analysis and use the width and the height of each beam as information. So what I want to 3D print is the formwork or the voids to create those beams that I will then cast in place in situ. So I generate the outer boundaries, the voids, and I allow each wall of the void to have the height of the corresponding beam. One of the first things I take into account is that these voids will be capped. We'll have a ceiling over which I will pour my concrete. So I want to avoid having too much effort on top of it. So in order to increase the rigidity of the piece, I will increase the density and within the same shape, generate an extra rib to increase the rigidity. So now I don't have, my piece is stronger. this shape is able to respond to one of the constraints of oriented-less pressing or the concrete reprinting at X3, that it has to be a continuous path. So it's not easy to see, but each shape has a single wall that loops around to create the shape. And I'm starting also to think on how to improve that 3D printing process that embedded with additional items that would allow me then to pick up and to place in situ my pieces. I also, if you can see the change on the shape from one slide to the other, what I'm doing is to also improve the shape of the pieces to be able to increase the printing velocity. This is because the robot can make a more fluid movement, so I can print faster and therefore reduce the time it takes. And I'm also taking advantage of one of the great potentials or capabilities of the X3 printing system, that I can print non-planar shapes that have a variable height. So because my beams had different heights, I can adapt to them with my 3D printing system and have a one continuous loop that is able to change in height. So then I get my individual pieces, then I can even more analyze the structure of them and decide the properties for the 3D printing. In these cases, the thickness of the lace. If, for example, I see in my structural analysis that the piece is very stable and not very fragile, I can reduce the thickness of the wall to be able to reduce material and print faster. And the idea of this, so as you see, I have just the boundary, but I'm still missing the cap. And I didn't go into that into my project, but here I just showed that on top of it, we could possibly cap it with an additional element that can be either 3D printed, or in this case is also digitally manufactured, and we can add more performance to it. Like in this case, it can have some acoustic properties as an example. And so I create this, for example, wood elements that I placed on top of my pieces, and then I can cast. So this is like a resume of the different elements of my slab. I have the performing top that it can be made of wood. This is my 3D printed element with the added ribs. And this is in light gray, this is my casted concrete. And I also show that the different different beams can have different heights. And here I need to include a temporary support to be able to place my pieces on the shores, on the building while it's being constructed. So this can be also 3D printed in a more reutilizable material that is easy to destroy and reuse easily, like for example, clay. So I generate these supports, and what I do with these supports is to place them on the shore, on the shoring for the slab. Then on top of them, I put my 3D printed concrete pieces. And when I have that, I can add the rebar for the reinforced concrete. I add my wood panels that have below the performing texture for acoustic performance. And once everything is in place, I can cast my concrete on top. So this is the different steps that I just showed. I have the scenario, I get some initial information, I optimize my shape, and then I generate the shapes for the robotic 3D printing. And in order to improve and optimize my 3D printing process, I created the last step of the framework, that is to generate automatically the analysis mesh from the toolpath, from the robotic toolpath. And then I use it in my script to assess the behavior of the mortar and the stability of the piece while it is being printed. So of course, it describes an iterating process that I go layer by layer, studying how the concrete will behave, and if while it's being printed, if I will have any stability problems. And from that info, I can take multiple decisions about my shape or the printing parameters. For example, I can see that if I increase the thickness of my layer, I can be more stable and possibly print faster. And also, if here I see that if I print slower, my piece is more stable. So I can have like that play to, okay, I want to print as fast as possible, so I will increase a little bit my layer width, and then I can print very fast. Or I want to be very stable, so I know that I need to print at this specific speed in order to reduce the material and still be an stable piece. And so, yeah, these are the three main components of the design framework I developed at Paul Depot along with X3. Yeah, and that's it.
Mm-hmm. Thank you.
Thank you very much, Felipe.
Yes. Yes. Bawana, can you hear me?
I mean, is French mandatory enroll for the program?
No, the program is in English.
Okay. But I believe for the visa procedures.
Answer, French is not mandatory, so the program is taught in English, but French can be useful some days. French can be useful to get by in the city, and yes, and at the Department of Advanced Master, we can provide some support to improve in French as second language. Yes, please.
Okay. And the second question we have from Ms. Jasmine is how we can collaborate to have our students a semester with École des Ponts. The students would be bachelors in architecture. And one more question I have from one of the faculties who teach interior design, I mean the space design, which we call it Anand, that can some of the students who are interested can join one semester or one program in between their studies to do any course or anything into building design or structures or you know, any other thing. So
sorry, I'm not sure I understand the question.
Okay, the students who are studying, because at Anand we have architecture, the architecture program usually in India is of 5 years. Mm-hmm. And I believe in France it's of 3 years. Mm-hmm. And in between our program, our students go. So our students go for an internship. I mean, work under an architect for a good 6 months. Okay, that is in their the 7th semester is their internship semester, and their 10th semester is their thesis, the final year thesis. So, is there any arrangement we can have that any of the students who can study for a semester, maybe for the buildings or structures or something?
Yes, I think it would be possible to do only the 2nd semester, but I will say that it is I think quite difficult for somebody who has not, learned anything of this field before.
Yeah.
Usually we try to recruit people that have already finished their studies.
Okay.
It's
what
a professional
I can do is
training.
I can share the program detail of architecture with us to you, and you can just have a look into it, and you can suggest that yes, at this point a student can be because mostly students they are more mature after their sixth semester. They know a little more and they're mature enough. At the same time, they want to explore something else, because from you can say 2nd May to 6th of June, students are going to France, Spain, and one more country for a study tour organized by LX Foundations or something. So they would be studying one week each under a mentor, and 1 week of the cultural tour they would be having in Europe.
Okay.
Yeah, you can share the details, Paola,
Yes,
and we will
pleasure.
look into it. Yes.
Hello?
My name is Parth, and I am in foundation year in Bachelor's of Architecture in Anand National University. So I am not into the construction methods yet. What you have discussed is so amazing, and half of it it was so nice and complex that it went through me. But I really want to know, as an architect, the process through planning till the end of the construction of the structure. How, as an architect, do you think? So it may be helpful for me in future as an architect.
You mean planning the deconstruction? Is that it?
Yes, sir. Planning, then execution of it, and how you encounter and solve the problems that came into the way of your construction.
Okay. Yes, this is indeed a very current theme of work, and this is something that is associated with some of the research that we have at school. And in the master, there is a workshop at the 2nd semester taught by Myriam Daligna, who is a former member of Norman Foster Architects, that focuses on conception and design for reuse and deconstruction. And this is something that is also explored through courses of environmental impact analysis that we are focusing on in the master. I don't know if this answers your question, but this is a difficult question, of course, deconstruction.
Sir, it kind of, but can you suggest any reading material for me?
I'm sorry?
Can you suggest a reading material for me so I can understand it in a deeper manner?
Reading material.
Yeah, I think I can. You have. I'm working. I can write in the chat the name of a researcher. This is an example. There is a researcher that has made some nice article to be introduced to this that is called Jan Bruting in EPFL, the Polytechnical School of Lausanne in Switzerland. I think this, if you go on ResearchGate, you can get some articles, and from these articles with the bibliography, you can get some other articles, and this could be a way to enter the subject.
Yes. And
for example,
on the website École des Ponts, you have the digital building design pages where you also can find a contact to follow up if you need more information on the program and how to apply also.
one more question.
Yes.
So like what I think I saw in the construction, like the structures in the presentations, is the geometrical beauty, the mathematical beauty of the curves that are like what I saw. So my question is like, how, as like a designer, you imagine it and you design it. Do you use an advanced mathematics or some computer generated stuff?
Yeah. So if I understand your question, is how do we involve advanced mathematics in the design of objects that require it? Is that it?
Yes.
Okay. Sorry, I have a bit of trouble hearing. Yeah, so there is, it is of course something that is a bit, you know, difficult, especially if you are an architect with a few mathematical background. But we have a dedicated course inside the master that is meant to be understood by everyone. And the purpose is to be able to, you know, understand the basic concept behind those mathematics and to be able to apply them thanks to numeric tools that we explore with softwares. So the idea is that we practice to be able to understand those concepts. Am I answering your question?
Yeah, sir, but like to know it more for my like future work, I think the same thing. Can you suggest some other reading material regarding this topic?
Yes, so I can give you the name of the teacher for the architectural geometry. He's called Romain Ménil, and he has written many articles online. There is also the ThinkShell website, which is the website of the lab, where we put each work. A lot of Critica has been showing is on this website, and you have also reference in there. So I think this is a way for you to dig into this. And you can, of course, write me an email if you want. Thank you, Critica. If you want, you know, to get in touch and have more information.
Yeah, and if we continue to publish yearbooks with part of the students' project, I don't know if we plan to do it in the future. It can be interesting material for, yes. So we will keep you updated.
Thank you. Thank you, everyone. Like, I really enjoyed every presentation. I came to know about the like construction method, different like the use of technology and everything. It was really like wonderful for me. Thank you.
Right.
Thank you very much for your interest and your kind words.
Okay. Thank you.